Okay, so last time we talked about an example of a specific transfer function and looked at how, first of all, if we did a bodplot on MATLAB, that would look and what that meant, and then how to start the process of doing a bodplot by hand. And we worked through almost that entire example. What we want to do now is take a step backwards because once you understand that the general approach to getting a bodplot analytically is to convert your s's to j omegas, use the logarithmic scale for the magnitude plots, and take the log to put your magnitude in dB, that the plots then fall into certain patterns. So what we want to look at now is step by step, we want to look at each general type of pattern. So the first thing we want to look at is what happens if we have a transfer function that has a term s to the n. So in other words, it has either a pole or a zero located at s equals 0. So you might have an s or an s squared in the numerator, or an s or an s squared in the denominator. Because remember, in the previous lecture, we determined that bodplot effects are additive. So if we get the effects of several individual terms, since we've taken the log, we can add those all together and get a feeling for what the overall plot looks like because we're summing each term. So the first term that we want to look at is just a simple term like s to the n. Now if we substitute j omega for s, then you basically see that instead of s to the n, you have j omega to the n. And now if we take 20 times the log of that, which is what we're going to do if we're doing a magnitude plot, that'll be 20n times the log of the magnitude of j omega. Now this is very much like the previous example where we had 20 log of absolute value of j omega, which was just log of omega. And it basically ended up giving us a straight line plot with a slope of 20 dB per decade. The only difference here is that we'll have a slope of 20 n dB per decade. So what I want to do is to go to MATLAB and look at just some different examples of transfer functions with one term only, the term being some power of s. So let's clear all, and let's go ahead and close our figure plot from the previous example. And so now let's just look at an example where, let me write a comment here, and let's look at an example where h of s is equal to s. And then s squared, and so on. So here we would have powers of s in the numerator. So let's say the numerator is s. Then I enter that into MATLAB as 1 space 0. So that would be s plus 0. And my denominator will just make 1. And then let's do a bodplot of numerator, denominator. And we'll wait for it. My computer's moving very slowly here. Okay, so here you see that basically you just have a linearly positive slope. Now one thing for me to point out, on the frequency scale of the bodplot, you see I have here plotted 10 to the 0 and 10 to the 1. There's no 0 frequency because basically this is a log scale. So you've taken the log, and remember the log by definition never equals 0. So basically you go to fractions of 1 radian per second on the left, and then powers of radians per second on the right. So your tick marks would be 1, 10, 100, 1/10, 1/100th going the other direction. So you don't ever reach actual DC. You're just getting lower and lower in frequency. Okay, so that's my h of s equals s. Let's now tell this to hold on to that plot. And now let's use a different numerator, numerator number 2. and let's use s squared. So there I would have 1, 0, and 0, representing s squared plus 0s plus 0. And now let's do a Bodie plot of numerator 2, denominator. And so what I now see on my plot is that s squared is plotting in red, and so it's going to have a steeper slope, which we would expect because s squared is a second order function. So it's giving us a steeper slope with respect to frequency. Notice the phase has gone from 90 degrees to 180 degrees, and we'll talk about phase in a separate set of lectures. So the magnitude plot is actually the slope has increased. We could show a trend. Let's go ahead and define a numerator 3 to be s cubed 1, 0, 0, 0. And let's do a Bodie plot of numerator 3, denominator. And so when we do that, you can see now we have the line showing in amber that represents that particular plot. Okay, now what I want to do is, now let's change the denominator. So now let's represent h of s to be 1 over powers of s. Okay, so in that case, the numerator, so let's just call it numerator, will be 1. And now we will have various denominators. So the first one, let's pick a transfer function that would look like 1 over s. So the denominator in that case would be 1 and 0, representing s plus 0. And now let's do a Bodie plot of numerator and our denominator 1, representing our first order. Okay, now you see what's happened if you look at the purple line. We have a 20 dB per decade slope, so it's going from 0 to 20 over 1 order of magnitude. But notice that it now has a negative slope. That's because that s term is in the denominator. Now, keep in mind that what we're seeing is only a portion of the Bodie plot. We're only seeing what MATLAB shows. So actually, this line continues. We're just seeing the window that MATLAB's default has selected to show us. So you could actually increase the range of your frequency axis on the plot, and you would see that these are all lines and they all cross right here with a 0 value at omega equals 1. You might spend some time trying to figure out why that is. Why would they all have a 0 value at omega equals 1? It's a fairly easy thing to see, but if you can answer that question, then you probably are understanding this. Okay, now let's say denominator 2. Let's go ahead and let this be s squared, so 1, 0, 0. And now let's do a Bodie plot of numerator denominator 2. And you're beginning to see the trend here. The green line is now showing this slope of minus 40 dB per decade. So that's what happens when we have terms that are only in S. Now the key thing to remember about this is, and let's go back to our PowerPoint slide, the key thing to remember about this is that in the case where we have a transfer function that has a pole or a 0 at 0, it's going to be that polar 0 that's going to determine the low frequency behavior of the system. In other words, whether there is no slope or a positive slope or a negative slope, and what the slope is will depend on whether or not there is an s to the n term present in the transfer function. Okay, so if we were to go back to our plot, if it were s to the 0, in other words, it was just a constant, what would you think the slope would be? If this is s to the 1 and this is s to the minus 1, s to the 0 is basically going to be flat. So if you have no s terms, no s to the n terms in your transfer function, the low frequency behavior is just a flat line with a constant gain. What the gain is depends on the other things in the transfer function. But basically, poles and zeros at 0 determine the low frequency asymptotic behavior of the Bode plot, independent of what else is in the transfer function. So at low frequency, those S terms will be the dominant terms.